I had several questions about dimensional analysis. It's over so you can see me a little bit. All right. So for example, we've defined done a few things. One is we've defined the change in X as X final minus X initial. This is displacement. This is a vector quantity. And it has magnitude and direction. And in physics, if we're talking displacement, this is a measure of length. So I think one of the things that people got discombobulated on the pre-work is the pre-work said, all right, so we've also said that velocity is equal to the change in position over the change in time. And it gave us a value that said L over T, where L meant a length and T meant a time. So velocity is a change in position over a change in time. So it's going to be a length variable divided by a time variable. So this could be in meters per second. Now, let's say I've done some algebra. I had a weird equation. And at the end of my algebra, I got a unit of meters, seconds divided by seconds cubed. That's what came about, which means that one of these seconds would cancel out, and that's going to be squared. And I've got meters per second squared. Well, we know this velocity should be in meters per second. That's not correct because that unit and that unit doesn't match. So when we talk about dimensional analysis, what we're doing is we're looking at our equations to find out, do the units make sense? So one of the problems we had the other day, we were using the quadratic equation. And when we used the quadratic equation, it gave us a value, we had our b squared minus 4ac under the quadratic. And that came from, we had a variable which was equal to an a times my variable squared plus a variable here plus some constant. And if this is a position or length or meters, each one of these has to be in meters. Otherwise, I can't add these three things together. I can't add apples and oranges. So if that's got to be in meters, then whatever I have here, whatever this variable is, let's say this is time, because that's what we are actually working with. That's time. Then A is going to have to be in meters per second squared in order for that to be meters, because A times T squared has got to be meters per second squared times second squared. So those cancel out. So that's got to be in meters. So you want to make sure that your units are matching up. So my units of B have got to be in meters per second, because B times T better be in meters. And I've got meters per second times seconds. Those cancel out. That's meters. This cancels out. That's meters. And my units are there. So what we did here is, if my B has to be in meters per second. So I got meters per second squared minus 4. And my A had to be in meters second squared. And my C is in meters. And all of this was under our radical, I get meters squared seconds squared minus meters squared seconds squared times 4. But my units are in meters squared seconds squared. So I get the square root of that, and I'm going to end up with meters per second. So that's when we say dimensional analysis is going to save you, because we can follow the units and we've known we've done our arithmetic correct. So when we're doing dimensional analysis and we're tracking our units, it's going to let us know, did we screw up something? Which is exactly what happened to me in the video on Thursday or Friday or to Wednesday, whatever day it was. We had that there. So that gets us back to one of the other questions I had. I had a person that says, it's been a hot minute. I've slept since then. I don't remember the quadratic equation. Well, this is why we play with algebra. So the quadratic equation is that x is equal to minus b plus or minus the square root of b squared minus 4ac all divided by 2a. And where this comes from is if we have our parabola, and we've got this, that we can define this curve and plot that curve by using an equation that 0 is equal to some value a squared plus b times t plus c, where this is the coefficient of our values. Oops, that's not a square. That's just 1. And if I use this equation and I plot, I'm going to get something that looks like this. Well, because I have a square, that means that we have 2 solutions. If I have a cube, I'm going to get 3 solutions. But I've got 2 solutions. Now, in algebra, what we did to you is we did all kinds of horrible things, right? We did a ton of horrible things. We said, solve this, and you had to do this. You had to do 0 is equal to some value. We're going to give it a d minus t times an e plus a t, where d and t are some constant like this. And we got our 2 solutions this way. Then we did it another way. Then we did it another way. And then we did it another way. We beat on you in college algebra to get you to solve this over and over again. But then it was like, well, if I have this equation is always going to solve that right there. So the question is, why did we do this to you in college algebra? Because when I grew up, we didn't have a calculator like this. I remember when the first calculators came out that were add, subtract, multiply, and divide. We had slide rules. So in order to do things, we had to go through this whole rigmarole in order to be able to solve these problems. Now we just punch it into the calculator, we put it in the quadratic equation, and life is great. I would recommend that you review, I think it's Appendix A. In the text. It's got example problems. It's got a variety of things in there. It's got a whole bunch. But that's why we go through this whole thing to do our quadratic equations, but we have 2 solutions because we have a square. And again, it's probably because of some of you, it's been a hot minute since you've done college algebra. So hopefully that addresses one of the questions. Yeah, so I had a lot of questions about that dimensional analysis question. I had a lot of questions about the other ones, but we also had questions about a problem that looks like this. So give me a second. and I'm going to write it out because I want to write it out for a reason. We said we have an arrow that is shot straight up. And we're given at an initial speed of 12 meters per second. After how much time is the arrow heading downward at a speed of 3.00 meters per second. Okay. So if you happen to go back and review the book, it gives you a way to deal with the problem. First, we want to read the problem. So we read the problem. We got an arrow that shot straight up at an initial speed of 12 meters per second. After how much time is the arrow heading downward at a speed of 3.0 meters per second? Well, we also have a toolkit. So let's write down our toolkit. We have that velocity squared is equal to initial velocity squared plus 2a times my change in position. We have y is equal to 1/2 the acceleration times time squared plus my initial velocity times time. And we can write that as the change in y. Or we can write that as the change in x. These are just positions or displacement. And we have v final is equal to v initial plus my acceleration times time. Now we're in one dimension. So one dimension can be up and down. One dimension can be right and left. I can also do one dimension on an inclined plane. And my one dimension can be up the plane or down the plane. I'm just traveling in one dimension. So any of these equations we can use for one dimension. The other thing is v initial, this is my velocity initial, is a value. It's not a variable. When I'm setting up this problem, whether I have a velocity or not, it's a variable or it's a value. I've started at 12 meters per second. So that value is going to be something that I put in. Now we're in General Physics 1 and we're going to be nice. And we're going to say acceleration is a constant. Now, it can still be a variable because if I'm in my car and I'm at the stop sign and I put my foot on the accelerator pedal, there's a reason we call it an accelerator pedal. If I put my foot on the accelerator pedal and I hold it steady, it's going to be a constant. We're not going to have any variability in that acceleration. We're going to tell you it's going to travel at 3 meters per second, or we're going to tell you it travels at 4 meters per second, or we're going to calculate it. It may be something that we have to figure out. So when I look at these problems, my variables that I have, my variables are velocity, position, and time. But my initial velocity is not a variable. I'm going to be given that. My initial position probably won't be a variable. I may be given that. A lot of times it'll be 0. But I have 3 variables: position, time. Now, if we go back to our problem here, let's read the problem. So we're going to read it again. I got an arrow that shot straight up. It's got an initial speed of 12 meters per second. After how much time is the arrow heading downward at 3 meters per second? So let's think about what this is going to do. So we're going to toss a ball up, and it's going to come back down. And that's what it's going to do. This is the trajectory of our ball. Well, of our arrow in this case. This is an arrow. This is the trajectory of our arrow. So we're going to draw the picture because it's going to help us understand what's going on. Now, there's something in the problem that they've given us that they're assuming that you know. And the assumption that they're assuming is if I'm tossing a ball, a golf ball, an arrow, I'm going to have an acceleration that's going to equal my acceleration due to gravity. It's going downward, and it's at a constant of 9.81 meters per second squared. So while my problem didn't explicitly state that, it says it's shot straight up, it's heading downward, and we're going to make the assumption that we're on planet Earth. And by making that assumption we're on planet Earth, that's the value that we're going to use. So if I'm coming here to draw my picture, I'm going to use my acceleration due to gravity. I'm going to use an arrow that says it goes down, and I got 9.81 meters per second squared. I'm also going to put in some information that we know. We know we're starting up, so my initial velocity is 12 meters per second. And we're trying to find at some point here, we want to know the time. This is our unknown. This is what we want to know when the velocity is equal to a negative 3.00 meters per second. And the negative comes from we're going downward. So my negative's going downward. We've got this up. But I want to stop here and I want to highlight something because we can. And it's a good time to do it. We also know something about this particular situation because we know something about what's going on fundamentally. We actually know what the velocity is at the top. We know what that velocity at the top is. Because as I'm going up and all of a sudden I'm coming back down, that velocity at the top has to equal 0 meters per second. Because at the instant I reach the arc at the top and I come back down, I have to instantaneously stop because I'm changing direction. So when we're looking at some of the other homework problems and we're working on some of the stuff that we're getting into chapter 2, we actually know what that velocity at the top is. That velocity at the top is 0. I don't have to know it for this problem, but there are other times that we may need to know that the velocity at the top is equal to 0. So let's look at our toolkit. We want to find time. So let's look at what we know. So we know our initial velocity is a positive 12.0 meters per second. we know our final velocity is minus 3.00 meters per second. We know our acceleration, and our acceleration is a negative 9.81 meters per second squared, and time is what we don't know. So let's go back and let's look at our equations. Well, we got velocity final, we got velocity initial, we got acceleration. I know nothing about position. I know nothing about position, so that equation is not going to do me any good, because this equation is in velocity final, my initial velocity, I'm in an acceleration, and I'm in x. That's not my variables down here. This one, I'm in my position, which is an x. I've got acceleration, I have time, and I have initial velocity. I don't have final velocity. So that equation's not going to help me. This equation, I have final velocity, I have initial velocity, I have acceleration, I have time. Voila! This is the equation that I'm going to have to use. So when people ask, I don't know when to use the equation. Well, if I write out my things in all its gory detail, which is what I've done here, I've written it out in all its gory detail, I know, oops, this has got to be the only equation that I can use because they're my variables. So we'll start with that. So let's write it around. So now we write down the equation that we need. We got velocity final is equal to velocity initial plus my acceleration times time. This is what I need to know. So we need to solve for t. So now I'm going to do velocity final minus velocity initial is equal to velocity initial plus my acceleration times time minus velocity initial. Those go away. Velocity final is equal minus velocity initial is equal to acceleration times time. Up, I got to divide both sides by acceleration. So now I get velocity final minus velocity initial divided by acceleration is going to equal my time. So now my velocity final is a minus 3.00 meters per second minus 12.0 meters per second divided by negative 9.81 meters per second squared has got to equal a time. So let's do the dimensional analysis. I'm going to do the dimensional analysis separate. So I have meters divided by meters per second divided by meters per second squared. This equals meters per second, second squared meters. That cancels, that cancels, that cancels. And I'm in seconds, so I've done my algebra correctly. I have a way to check my algebra. So let's do the numbers here. I got minus 15 divided by minus 9.81. I'm in seconds, so life is good. So I'm going to take, clear everything. I'm going to get 15 divided by 9.81. And I get a positive 1.53 seconds. And I've solved the problem. It's asked me at what time is my arrow at a velocity of negative 3 meters per second. So I did this in a lot of gory detail, but I think that kind of gets you a couple of questions that people were asking. When do I know what equation to use? How do I go about using my dimensional analysis? How do I actually read my problem and pick out the information that I have to have? Okay. So let's do another fun one. So we've got a car at the stop sign. So there's my stop sign. We want to know the distance. That's what we want to know. We want to know the distance it takes to have my car reach a final velocity of 25 meters per second. Okay, we want to know the distance that it takes to reach a final velocity of 25 meters per second. If it takes we'll do 1.3 seconds. We're starting at a stop sign. Anytime it says we're starting at a stop sign, that tells me my initial velocity is equal to 0. So I'm looking for words at a stop sign or from rest. That means I'm starting with initial velocity of 0. So what do we know? We know our final velocity is 25 meters per second. We know our initial velocity is equal to 0. We want to find distance. And we are given that time is equal to 1.3 seconds. So I have my equations. Okay, I have my equations. I have V final squared is equal to V initial squared plus 2A change in position. I can rewrite this as 2AD. So there's one equation. Well, let's look at what I've got. Okay, I've got V final, check. I got V initial, check. 2 doesn't have to worry about it. I'm looking for D, that's what I need. A. Nope, I don't have an acceleration. Bummer. All right. I have a change in position is equal to initial velocity times time plus 1/2 AT squared. All right, well, I'm looking for change in position. That's good. I got initial velocity, check. I've got time, check. I don't have acceleration. Oh, bummer. I also have V final is equal to V initial plus acceleration times time. Well, I got V final, check. I have V initial, check. I have time, check. I can find out A. Well, that's great because I can use this equation to determine acceleration. And once I have acceleration, oh, I can plug that right into there and use that to go into there. So let's solve for acceleration. So I got V final minus V initial divided by time is going to equal acceleration. I have my V final is 25 meters per second. My V initial was 0 meters per second. I'm dividing time of 1.3 seconds. This gives me meters per second squared. My units check. My units are all good. So now I can figure out my acceleration. I get 25 divided by 1.3. And this is an acceleration of 19.2 meters per second squared. So now I've got that. Well, now I can plug into this one. My change in position is equal to my initial velocity times time plus my 1/2 my acceleration times time squared. So this is 0 because that initial velocity was 0 plus 1/2 my 19.2 meters per second squared times time squared, which was 1.3 seconds squared. Second squared are going to cancel out. So I'm doing really good. Leaves me with meters. That's really good. So now if I do that, it's going to take 16.25 meters to go from 0 to 25 meters per second. If we're doing it in 1.5 seconds, and I've calculated the acceleration. So we've been able to look at our one-dimensional motion. Able to look at our one-dimensional motion. Any questions? All right, we're going to do one more, and then we're going to call it a night. So I have a building. We're going to throw a ball up and have it come back down. Okay. We're going to give it an initial velocity of 1.5 meters per second. We're going to draw windows on our building here. We're going to give ourselves the height of the building. We're going to give this as a height of 48 meters. It's always a bad thing when I'm making up numbers on the fly, but we're going to give it a height of 48 meters. There's some things that we know about the problem. We know that we have an acceleration due to gravity that's going down 9.81 meters per second squared. We've got initial velocity going up. We also know something about the top. We know the velocity at the top is going to equal 0. So we've got that part. So I can ask questions like this. What's the distance that it takes the ball to go up to the top? I have my three equations. Velocity final squared is equal to velocity initial squared plus my acceleration times time. Wait, that's not right. This is my accelerate, 2 times my acceleration, 2 times my acceleration times my change in position. I have velocity final is equal to velocity initial plus my acceleration times time. I get my change in position. So this is going to be change in height is equal to my initial velocity times time plus 1/2 acceleration times time squared. Well, if I want the distance that the ball goes up, I know my final velocity is equal to 0. I know my initial velocity is equal to 1.5 meters. I know my acceleration is equal to a minus 9.81 meters per second squared. And I want to find the change in position. That's what I want to find. So I can get that. So I get velocity final squared minus velocity initial squared divided by 2 times my acceleration is going to equal my change in position. So I get 0 minus 1.5 meters per second squared divided by 2 times a minus 9.81 meters per second squared. This gives me meters per second squared meters squared second squared divided by meters per second squared. So I'm in meters, so life is good. So I get my 1.5. And it's going to be 0.076 meters. So I'm obviously not drawing this one to scale. because it's going to pop up and it's going to come right back down. We want to know the time of flight for when it hits a position of, this distance is 36 meters. So it's going to fall 36 meters. I can approach this problem a number of ways. We can do exactly what we did with the arrow, but I have to know my velocity at this point. We can utilize any one of these equations to get here. I can take the time that it takes to fall this much, and the distance that it would fall is going to be my 36 meters plus my 0.076 meters. So I'm going to get 36.076 meters and that will give me the time that it takes to fall, just that part. I can calculate the time that it takes to go that high. All right. We know that V final minus V initial divided by acceleration is going to equal time. So I get V final is equal to 0 minus my 1.5 divided by my minus 9.81. And this is going to be meters per second divided by meters per second squared. And this gives me 0.15 seconds. So now I can figure out the time that it takes to fall, that part. So if I do that one, well, we can find out the final velocity. We can do that part. Oh, let's do this one. We're going to get my change in height is equal to my initial velocity times time plus 1/2 AT squared. But if I use at the top, that's 0. So I get 2 times the height divided by my acceleration is going to equal t squared. So the square root of 2h divided by the acceleration is equal to t, which is going to be the square root of 2 times 36.076. And that's in meters. And my acceleration, and that's a negative, because I got a negative 9.81 meters per second squared. And this is negative because it's going down. And then I got to take the square root. And that says the time was equal to be 2.71 seconds. And if I enter that into WebAssign, it's going to go wrong because I have to add the trip up. So the total time is equal to the trip time for up and the time for down, which is going to equal 2.886 seconds. I'm going to block that so you can see that on the piece of paper a little better. So hopefully what I've done is I've given you some examples, answered some of the questions that you guys had, and then gave you a couple sample problems. Tomorrow we'll start with vectors. Wednesday we'll look at the lab. And then if you've got any questions that you want me to look at before you do your quiz, send them to me via email or send them to me via a message. So at this point, I'm going to stop recording.